mathematics in this, let's say, interpretive way, not in the strict way, but with your interpretation, you need to define things very strictly. You have to write down things, what you want to be, how you require them to be, and then everything will be clear. There will be no problem. Another interesting thing is, we in Cartesian system, we generally say when we define a function, then x, the first coordinate, the abscissa, is the independent variable, and the ordinate is the dependent variable. However, when we deal with polar coordinates, we usually define radius in terms of the angle, but in the writing down, in the description of the coordinates, we generally write the distance first and the angle second. That's an interesting moment. You will discover it next semester as you.
Miss, the angle, right? The polar angle. Why you write it in a square bracket and under regular bracket?
Yeah, because this is, let's say, this is the minimum interval. And the minimum interval, if I write the square bracket, it means the same direction would be mentioned twice, because 0 and 2 pi, it's the same direction. So this is simply the minimum interval. The minimum interval that would include the full circle. It's the same here. Minus pi and pi actually end up being the same direction. So to avoid repetition, I excluded the minus pi. And of course, it's always more useful, more convenient to use 0 and not 2 pi, and more convenient to use positive pi rather than the negative pi. That's how I choose.
But usually, the intervals are only represented with the square brackets, right?
The square bracket is for the included point, yes. But in this case, let's say to describe the minimum possible situation, without repetitions, one of the ends should be round bracket, not included, because it already would be a repetition.
Okay, so minus pi will not be included, and 0 and 2 pi will not be included. That's the
because that's more convenient. Of course, you are perfectly allowed. You may say, okay, I want phi to be from 0 not included to 2 pi included. It's of course perfectly allowed.
Okay.
But it's not so convenient. It's not so convenient. So oftentimes we think about what is convenient, not only what is strictly mathematically perfect, but also what is more convenient for us.
But will both of them be equal?
Perhaps not. Depends on what we want to do with this. If we want to find simply the location of a point, then of course it doesn't matter whether I write point A coordinates 3, 2 pi, or point A polar coordinates 3 and 0. It would be the same point.
Okay.
It would be the same point. So of course it's more convenient to have 0. That's the whole thing. That's the reason.
Okay, sure. Thanks, Miss Tank.
Okay, now we move on. And now the next thing is, so how do we convert the coordinates? So about the conversion of coordinates. So I draw these lines on the slides. I include the lines so that I don't overstep boundaries, so that I leave space. I know that there will be something coming up here in the top bottom corner. But at the moment, so let's go and consider to convert between polar coordinates and rectangular coordinates, Cartesian coordinates. We assume that the pole is the same as the origin of Cartesian coordinates, and the polar axis is the same as the positive x-axis, and then a point could have polar coordinates, let's say r, phi, or it could have Cartesian coordinates x, y, different systems. So I could say A Cartesian or A polar, and I would need a darker pen. See, in polar coordinates, I would describe this point as at the distance r and angle phi from the pole, from the origin. And in the Cartesian coordinates, I would say the coordinates are x and y, rectangular coordinates. So they are completely different things. So how do we convert? Okay, let's start with polar to Cartesian. So suppose we have the coordinates are, okay, no, a different pen, right, r and the angle phi. So as we consider, for example, this triangle, we know that in a right triangle, the adjacent leg, that would be the leg x, is the hypotenuse times cosine of that adjacent angle. So that would be r times cosine of the angle. If we have the angle phi, adjacent to the x side, to the side x. So r cosine phi, as we can see. And similarly, the y coordinate, it is the opposite leg to the angle phi, would be hypotenuse r times the sine of that angle. So this is actually how, if we have polar coordinates, we can find the Cartesian coordinates. There they go. Very, very simple. I know the distance and the angle, I can write x and y. Now, how do we get back? How do we get back? If we, supposedly, if we know the x and y coordinates here, if we know the coordinates x and y, then again, if we look at this right triangle, we understand, of course, according to the Pythagorean theorem, x squared plus y squared will be equal to the r squared, the distance square. That's one thing. And the other thing is, now what about the angle? So if we want to use x and y, then I would say, all right, tangent of the angle must be opposite leg, that is y, divided by the adjacent leg, that is x. There is a little bit of a problem, because if x and y are both positive, might have the same tangent value when x and y are both negative. So that is a slight problem. So in principle, we also should note the quadrant. We can write many different things, all kinds of things, but we could say, for example, if both coordinates are positive, for example, we could look at the x coordinate. So for instance, if x is positive, it means the angle, if x is positive and, for example, y is positive, as in this case, then the same tangent would be according to this angle. On the other side, the symmetrical thing, x, instead of x we would have minus x here, instead of y we would have minus y here, but the size of the triangle is the same, the angle is not exactly the same. So we could say that this is actually the arctangent of this value. So normally, if x is positive, then we could say that the angle is arctangent of this y over x. On the other hand, if x is negative, then we see we have to go to the opposite side. And in that case, if x is negative, then we could say that phi is arctangent plus or minus phi. That would be half a revolution. Well, in this case, it would be back. In this case, it would be assuming that the angle is from minus pi to pi. This can be, there can be some variations. It's not the one and only way of writing down the correct angle for any coordinates. In principle, in practice, when we need to do this in practice, we do, of course, we do the distance r from the coordinates, so, or r would be the square root of this, of course. The distance is the square root of x squared plus y squared. We would do this, and then we would say, all right, we find the angle for the tangent, but we also need to note the quadrant. We need to note the quadrant. In principle, that would be, if we see that the x value is negative, then we choose the angle from the left half plane. From the left half plane. If x is positive, when we look at the coordinates, we note the quadrant from coordinates, of course.
Yes. Do we take consider of the y values as well if the y value is negative?
That would be perfectly enough, because the thing is that arctangent is defined for the right half plane. If you remember anything from trigonometry, arctangent is defined. The range is from minus pi half to plus pi half. The values of arctangent belong to this interval of angles. So that's why I take when x is positive, we take the arctangent as it is. But if I need
Okay.
negative x, then I have the diametrically opposite point. That's the
Okay.
reason why I discuss x is positive, x is negative, but not y is positive, y is negative. In practice, there's nothing to stop you doing, okay, let's have a look at both coordinates. Let us see which quadrant we have. And then according to that quadrant, we will decide the angle from the tangent. You don't have to think about our tangent necessarily. You can look
Okay.
at both coordinates, at both sides. You see which quadrant you are in, and from that quadrant, you will make the final decision about the angle. The tangent will help you decide the size, degrees or radians, and the y and x signs, both if you like, from the quadrant will help you decide the, let's say, the greater accuracy of that angle.
Miss, but I have a question, right? You know, like from trigonometry, right? The when x and y are both positive, it will be all sine, tan, and cos will be positive, and when it is in the on the right hand side, on the top right hand side, it will be only sine positive and cos and tan will be
Yes,
negative.
you have to be aware. Yes, you have to be, of course, aware of the signs, but this also corresponds to the trigonometric circle, because in the first quadrant, both coordinates x and y are positive, and sine and cosine are positive. In the second quadrant,
Uh,
x is negative, yes, but cosine is negative,
yeah, so
and
cos
y is positive, yes,
and tan will
sine
also
will
be
be
negative, right? Only
the
sine will be
signs are
positive.
all corresponding. That's to some extent the beauty of mathematics, because we generally everything fits together. Everything fits together.
Okay,
That's
miss.
the
Because
that's
I remember in my school the teachers how in the first quadrant all tan, cos, and sine will be positive, and on the second quadrant only sine will be positive, and the
yeah, but
third quadrant.
that's yes. We do it slightly differently. We say for sine the trigonometric value is positive, positive, negative, negative. Cosine, we draw these little diagrams: positive, positive, negative, negative.
Oh,
And then tangent and cotangent would be plus minus plus minus. So it's basically it's the same. Basically it's the
okay,
same
right.
thing.
Yes, it's the same, but
It is
yeah.
it's the same thing. Okay, now all right. I'll try to find a good diagram of the, let's say, the graph paper for polar coordinates, because you know what the graph paper with the system of coordinates looks like. For Cartesian coordinates, it's all squares and two axes, and for the polar coordinates, you need to see the angles and need to see the distances. So the graph paper for polar coordinates looks something like this. At the moment, for this, I would prefer to ignore these numbers. I will probably say this is, okay, rename. I will renumber, because for our purposes, it's better, easier to see that this is 1, this is 2, this is 3, this is 4. Makes more sense. I simply was looking around in the internet and seeing what I could find that has, let's say, decent quality that we can use, and this was the best at the moment. All right. So now let's have a look. And so, plotting the points. Point A, coordinates 3 by half. So 3 units distance, that would go, okay, let's see, pointer. So 3 units distance, 1, 2, 3, and the angle is pi half, that is the right angle. So the point A would be here, angle pi half, right angle, and distance 3. So I will take now the pen and I will map. This is the point A. Distance 3, angle pi half. Similarly for B, distance 2, but the angle 3 pi over 4, that's 135 degrees. So, okay, where's my, looks like here, well, 5, and here we have 9. It's every 10 degrees. It looks like this is every 10 degrees, so 45 degrees would actually be this direction. This would be 45 degrees. So for point B, distance to 45 degrees, it's this one, because it looks like this is 10 degrees, 20 degrees, 30, 40, 50, 60, yes, every 10 degrees, as you can see. So this is not perhaps the most convenient for us. So we have to understand that this would be actually 135 degrees. So that's between the two radius lines. So this is the point B. Distance 2, angle 3 pi over 4. And find our Cartesian coordinates. So convert to Cartesian system. For the point A, the Cartesian coordinates would be, we understand the x coordinate is 0. We don't even need to use a formula because we see it with our own eyes. The x coordinate is 0, the y coordinate is 3. But of course, we understand also that the radius 3 times cosine pi half, that's 0, that is x. And 3 times sine of the angle, which will be 1, is the y coordinate. So of course we can use the formulas, but in this case it's so obvious that the formulas are unnecessary. For the point B, let's remember that sine of 3 pi over 4 positive, square root of 2 over 2, and cosine of the same angle would be negative square root of 2 over 2, which means now, and the radius, the distance is 2, multiplied by 2, so we have the Cartesian coordinates for B would be minus root 2 and simply root 2. So if we just projected the point B to the x and y axis, we would get these numbers, minus square root of 2 and plus square root of 2. So these are the polar coordinates and these are the Cartesian coordinates. So simply getting an idea. So at the moment we're simply getting an idea. So you will hopefully in mathematics part 2 get a better idea of how to define functions, how to describe functions in polar coordinates. We will focus on Cartesian coordinates because the content of mathematics 1 requires those. All right, more plotting. So 4 pi over 4. Pi over 4, remember that's 45 degrees, so 1, again, I will say again, oh no, I will leave these numbers as they are. Okay, erase and take something bright, like red. 4 pi over 4, so 4 is somewhere there, the distance is 4, and pi over 4, 45 degrees, so it will be 1, 2, 3, 40, and 45 degrees is there. So this would be the point A. Point B, 6 and minus pi over 6. Minus pi over 6, that means minus 30 degrees. And the distance is 6, and then we go 1, 2, 3, this is minus 30 degrees. This is the point B. This exercise does not ask us to change into Cartesian coordinates. C, 8 pi. So the distance is 8, but pi it is the negative x-axis. So distance 1, 2, 3, 4, 5, 6, 7, 8. This is the point C, because the angle here, you see, this is the angle pi of 180 degrees. And finally D, 13 and 2 pi over 3. 2 pi over 3 is 120 degrees. So, all right, and 13, so 13 would go along this arc, until we reach 130 degrees. So 90, 100, 110, 120. This is the point D. So this is how we, let's say, learn to plot the points, how we plot the points in the polar system of coordinates. Now, let's go on. The next one, symmetrical. Find the coordinates of the points symmetrical with respect to the pole and with respect to the polar axis. Remember that the polar axis goes in the positive x direction. This is the polar axis O, and now. In this case, 2, 3, 1 is the radius, the distance, so I will again probably rename. I will probably rename these 1, 2, 3, 4, 5, so that it's a bit easier for us to see what is going on. So the point 2 and pi third. 2 pi third, that's 60 degrees. That would be here. Point A is this. Now, the point symmetrical with respect to the pole, it means if we simply go, it's the diametrically opposite point. We follow the same line, the same from minus pi to pi. If I decide that I prefer angles from 0 to 2 pi, then I would need to add pi to reach this point, to go on in the positive direction. And with respect to the polar axis, again, we have to think, so that would be go, symmetry, go, symmetry, go, and we would come to this point. That will be A2. And so A2 would have, again, the distance, it seems, is exactly the same again. So these symmetries do not change the distance from the origin, they do not change the R value, but they certainly change the angle. So if the original point has angle pi third, then the symmetrical point will have the opposite angle value. We are simply going, as in trigonometry, in the opposite direction. So we will have 2 and minus pi third. So similarly, for the symmetrical points, we don't even have to plot the other points in order to figure out the system. So if the point B has coordinates 3 and minus 3 pi over 4, that would be, well, 3, 1, 2, 3, it would be this point, minus 3 pi over 4, then evidently what pi will make it simply pi over 4. Because if we are dealing with 2 points that are diametrally opposite, the angles are diametrally opposite, we either subtract pi, half a revolution, or we add pi to the angle, and that's it. And the second point, the point symmetrical with respect to the polar axis, that is, we do the symmetry above the horizontal line. The distance is again, of course, still the same, but now instead of a negative angle, this is a negative angle, we will have the positive angle, 3 pi over 4. We are simply going in the opposite direction. So you see there's a lot in common with trigonometry. Really many things in common with trigonometry. But for C, now for C it should be, again, easy enough. So C1, with respect to the pole, we would need to go in the opposite direction. But we have 4 pi over 3. 4 pi over 3, that would be this angle. And with respect to pole, we subtract pi so that we get a negative, 4 pi over 3 is here. So this is 4 pi over 3. So 4 pi over 3 is this angle. To get the opposite, evidently, we should probably subtract pi, because this is already greater than pi. So we subtract pi and we get 1 and only pi third. For this, we actually see that it's because this is already greater than pi. The angle is already greater than pi. So it does not apply. They have assumed that the angle is from 0 to 2 pi. So this would be the symmetrical point with respect to the pole, and with respect to the axis. We could think, well, minus 4 pi over 3 absolutely doesn't make sense because it's negative and it goes too far back. But if we think that we need to go symmetrical, we need to go to this quadrant, actually it was this. We need to go to the second quadrant. This means that evidently we would simply consider what this angle is. If this is 4 pi over 3, which is not 4 pi over, I'm very sorry, I'm messing things up. I will erase the wrong things. I know I am messing things up a little bit. 4 pi over 3 is a little bit different. 4 pi over 3. So this is 2 pi over 3. This is 3 pi over 3. And the next is 4 pi over 3, that is here. So this means that when I want to do the symmetry with respect to the horizontal axis, then I say that this angle should be 2 pi over 3. Again, the diagram looking at the system of polar coordinates might be helpful in order to write the angle down more directly, more easily, without any formulas. So it's 1 and it's 2 pi over 3. So this is simply to understand how the symmetry works. It works either by adding, subtracting pi, or perhaps by simply changing the sign, sometimes even more simplifying than just changing the sign. For example, this involved more thinking than simply taking minus 4 pi over 3, because at this point, yes, we would have minus 4 pi over 3, but that would mean going all the way around, which is very, very inconvenient. So we would prefer to express this direction through 2 pi over 3, the remaining part, the corresponding positive rotation. So that is the same direction that I need, but using a positive angle rather than a large negative angle. It simply is clumsy, inconvenient, and so we think a little bit how to express it in a more convenient fashion. Okay, polar coordinates of 2 points in the...
Miss,
Yes.
in the test or in exams, right? Will how will we be drawing? Will we getting the coordinates or like what? How will be doing it?
If you have to draw anything, okay, yeah, online it's a bit more difficult. So if we did it on paper, I would simply give you a printed piece of these coordinates. Online, I have to think, but you will definitely, if you have this in an examination, you will have a system where to draw it.
Okay,
I will
so
figure out some solution to this so that you don't have to invent the system. You will have the circles and the radius lines and everything. So you will not have to draw this all completely by hand.
okay, sure. Thanks, Miss.
All right. Now, no graphing involved. Simply points and finding the polar coordinates of the 2 points. Of course, we could think of the Cartesian plane. We could actually imagine so that we simply have an idea what it looks like. Minus 5, 0, that would be this point, Cartesian coordinates, x, y, and 0, and minus 5. This is the point A in Cartesian coordinates. So in the polar coordinates, what should we do? Formally, we should say that evidently the radius square is x square plus y square, it's 25, so r is 5. Evidently, the distance is positive only. But we can already see the distance from the origin here. We can already see the distance is 5 because of the angle, because of where this point is. We already see directly. We don't have to waste time with this kind of thing. So it's 5, and the angle is very evidently 180 degrees or pi, and that's it. We simply look at this, we simply look at these coordinates, and we imagine where the point is situated in the Cartesian plane, and so we can imagine the coordinates of the point in the polar system. For B, we see that both coordinates are positive. So B is in the first quadrant somewhere, and we know that x is 2 roots of 3, and y is 2. So now in order to find the distance, we need to take the square root of this square, 2 roots of 3 square, x squared plus y squared. And in fact, we see that this is 12 plus 4, that's 16. So the radius is actually, the distance is actually 4. All right, so we have a distance 4 for the polar B, B in polar coordinates. The distance is 4. And the angle, now let's see, tangent of this angle would be y divided by x. So it's 2 divided by 2 square root of 3. That's 1 over root 3, or sometimes you can write it root 3 over 3. This means that because it's the first quadrant, then the angle is the arctangent directly. Arctangent of root 3 over 3, that's 30 degrees, or pi over 6. So from the tangent value, if you are using tables, for example, or a calculator to find the angle, it should be done in radians, but sometimes we can deal with degrees just as well. Just in this case, it's directly inverse tangent or arctangent of this angle, because I know that this is the first quadrant, so evidently this will be a small positive angle in the first quadrant. So this would in reality be pi over 6 or 30 degrees. This actually links also, this links together with the complex numbers. Again, something that you are going to have next semester. Complex numbers involving the negative, the square root of -1, the imaginary unit I. In fact, complex numbers are very closely connected to the polar coordinates. You will see many similarities, if not exactly the same formula. Now, equations of curves, like functions, well, not exactly functions, perhaps we are not dealing with functions yet in this course. So simply an equation of the curve. We see that x squared plus y squared, we already know in polar coordinates, this is radius squared, r squared. And the letter r is basically used because we consider this distance from the center the radius. We oftentimes talk about not the position vector or also the radius vector. Radius as in connecting the center to the let's say the end of the circle or the end of the vector. And on the right hand side, 6, and we know that x in polar coordinates would be r times cosine angle. And in this case, because we know that r is r is a positive number, we can divide both sides by r and say r is 6 cosine phi. R is 6 cosine phi. That's the equation of this curve, which is interesting because this is actually a circle that passes through the origin and has center on the x-axis. And at the same time, we can write it using the polar coordinates. So let me remind you a little bit how to get the circle. X squared, I am doing minus 6x plus y squared is 0. Remember that for the circle, and we already have established that last time we did it, x minus x of center squared plus y minus y of center squared equals radius squared for the circle, or we could say capital radius for the circle, to distinguish from this r. So if I change this into that form, I can think x squared minus 6x. To create the perfect square, I need to add 9. And so if I have 0 on the right hand side, I would still add 9 to the right hand side too, because I cannot change the balance. Both sides must still be equal. So if I add 9 to one side, I have to add 9 to the other side. And plus y squared. We can see this is x minus 3 squared plus y squared equals 9, that is 3 squared. In fact, we can even imagine this circle in the system of coordinates, the Cartesian system of coordinates. The center would be at 3, 0. The radius is 3, so the circle actually passes through the origin. And we see that we have the same equation in the Cartesian coordinates, and we can have the same equation in the polar coordinates. Even though the center is not at the origin, the polar equation is simpler. So in many cases, polar system is actually more convenient to use. We are very much accustomed to using the Cartesian system, and that's why we do it. But there are situations where the polar coordinates are better. Not all of them, not probably even the majority of all situations, but we can see that sometimes polar coordinates give a simpler equation. All right, now the next one. Radius squared sine cube phi equals 2. How do we deal with this? Again, might be somewhat interesting to consider. What would this look like? To resolve this, I would propose, let's take sine of 2 pi and use one of the basic formulas from trigonometry. That is the formula of the sine of double angle. 2 sine phi times cosine phi equals 2. Then we can divide both sides by 2, evidently 1. And now we can actually say r sine phi times r cosine phi equals 1. Or in other words, x times y equals 1. This is a hyperbola. So in this case, we see the Cartesian equation is simpler for this curve. So the hyperbola of this type, xy equals 1, is this something that should be again familiar from school? In this case, we see the Cartesian version is simpler and easier to understand and easier to use. So there are situations when one notation, one system is better, and then some situations where the other is better. More. Write the polar equation of the circle with the center at the pole P and radius 5. All right, we can imagine what it looks like. We know that it would be this circle. I'd rather for a following curves on this tablet. So what does this mean? It simply means the equation would be for all angles, the radius, the distance must be 5. That's it. This is the equation of a circle with the center at the pole P. You can call it P or O, it doesn't matter, and radius 5. So yeah, okay, that's it. R is 5 for all values of angle. This is an equation of the circle centered at the origin. Again, something extremely simple. Now, what is the curve defined by these equations? So phi equals, the angle equals pi third. That is, angle equals 60 degrees. Angle equals 60 degrees. Okay, let's count. 60 degrees is there at this point, so we have pi over 3. So in principle, all the points where this angle is 60 degrees or 3 pi on this half line. The thing is that at the origin, we do not have any angle. The point 0, 0, the point with 0 coordinates, actually this point does not have any angle. We are not considering it as having any angle at all. So basically we have a half line, a half line, not a complete line, because it only goes in this direction, pi third, but not in the negative direction, not to the opposite side. But that's it. Now the next, angle equals pi. Again, it would be similar to the previous case. So it would be the situation where the half line goes in the negative x direction. It would be this half line pi, that means going over there at 180 degrees. Again, not counting the origin. R equals A. We already understand. It's a circle with the center at the origin and radius A. So this would be simply a circle centered at the pole or at the origin and radius A. Sine of phi is 0.5. That's the point. Sine of phi is 0.5. What does that mean? That means that the angle is the angle for which sine is 1/2, but actually we see there are two such angles, because the angle could be 30 degrees, that is pi over 6, but also from trigonometry we know that there's another one where the sine value is exactly the same, and that would be 5 pi over 6, the symmetrical one. So if I have, for example, pi is 1/2, a sine of angle is 1/2 at this point, then we have to understand that we have an angle that has exactly the same sine value in the opposite side with respect to the vertical axis. So in this case, we have, first of all points on this half line, and then all points on this half line. So in principle, this is an angle with the center at the origin and going in these two directions. The sides go in these directions. But again, the center itself doesn't count because at the origin where everything is 0, we do not consider any values of angle. And finally, tangent equals 1. When tangent equals 1, so let's take that red. A tangent is 1, that means the angle is pi over 4, 45 degrees, but it would also be the angle minus 3 pi over 4, the diametrally opposite angle. So pi over 4, 45 degrees, that would be all the points in this direction, not the origin, because that doesn't ever count, and going in the opposite direction. Okay. 1, 2, 3, 4, this way. So basically, this would be a whole line, perhaps except that one point. This is a whole line. So in the previous case, this was an angle without the vertex. In this case, we have a line without 1 point. So minus 1 point, a line with a hole in the center, so to say. So these curves or straight lines, these objects are defined by very, very, very simple equations. Now, dealing with what comes next. Rewriting in polar coordinates some equations. So how do we translate equations from Cartesian into polar coordinates again? We did have some translation, and now we will have some more translation. This is quite obviously, we understand that this is the circle with the radius a. So we would say that this is, we could say r squared equals a squared, and we can say, okay, the distance is a if a is greater than, or maybe equal to 0. As to this, because r is the distance, we are normally thinking r is non-negative, greater than or equal to 0, as I just wrote down. So in what situations might we have negative r? So if the formula produces a negative value of r, then that might mean simply going in the opposite direction. Simply going in the opposite direction. You might see situations that arise when you have, for example, r equals, for instance, cosine of 3 pi. That would be, in fact, something very interesting. It would be an interesting curve. It would be something like this. But because cosine of some angles is negative, you would get negative values of r, which means you kind of go in the opposite direction. This is also possible. So generally, we assume that r is non-negative, but when we are describing some curves, it might happen that r becomes negative, which in our understanding will mean simply go in the opposite direction. Okay. Now, number 2, y equals x. I will choose something lighter and brighter. If y equals x, we already know, so r sine phi equals r cosine phi. If we use direct mathematics and we see we can divide out r if it's not negative, if it's not zero, and basically we see this is the line where sine and cosine are equal, or if we divide both sides by cosine, we get tangent phi equals 1. We already had it in the previous case. That was the straight line, except for the center. That was this straight line. X squared plus y squared equals ax. We already had something similar. This would, in principle, remember we had a was 6. And what we had, in order to complete the square, we had to take half of a. So this in principle would be, again, the circle. So r squared equals a times r cosine phi. Divide both sides by r. We have r equals a cosine. We simply express the x and y coordinates using the r and the angle, and then we simplify as much as it is possible. Where x equals 1, we could have, okay, r cosine phi equals 1, or we can say r equals 1 divided by cosine phi, that is r equals secant of the angle phi. And that's the vertical line. The secant function, it seems, the secant function actually in some sense is connected to that vertical line. With number 6, it would be very similar to this, only it would involve sine instead of cosine, because we would have AR sine phi. I'm not going to write this, but I would like to discuss number 5. That was this. Yes. I would like to discuss number 5 because this is one of the most interesting and, if I say so, most beautiful curves, which is called, let me state of Bernoulli. Lemniscate of Bernoulli. This is OU. B-R-N-O-U, Bernoulli. We will see what it looks like, but for now, let's try to translate this into polar coordinates, and let's see if that's something simpler. So x squared plus y squared, we already hopefully remember, it's r squared, and then square, and then we have 2a squared. We are assuming that a is a constant, and even that, let's take it positive. And here we have x squared minus y squared, that is r squared cosine squared minus r squared sine squared of phi. Now we see that we can divide out r squared, we can divide everything by r squared. So we have now simply r squared equals 2a squared cosine square of phi minus sine square of phi. The formula in the brackets should feel familiar. It is the cosine of double angle. R squared equals to a squared times cosine of the angle 2 phi. That's it. And that's it. And as we see, the polar equation of this curve is simpler than the Cartesian equation. Although, of course, we might consider, we might ask, so what criteria do we use to say simpler or not simpler? Not as many algebraic operations, or simpler algebraic operations, or it just looks simpler? That's another thing. So we have to see, because r squared has to be non-negative, it means cosine of the angle has to be non-negative. That means the angle 2 phi should be between, for cosine to be positive, between minus pi half and plus pi half. That is the angle phi itself. Now we are looking at domain of a polar function, which is interesting. So phi is between pi over 4 minus pi over 4, and that direction is this, pi over 4, okay, pi over 4, pi over 4, pi over 4. So the angle is actually, the angle should be actually here between these two. And as a result, what we actually get is a very interesting curve that looks like infinity. This is the curve that looks like infinity. And on the other side just as well, like this. What's more interesting, A and minus A. This point is A. So it's always, it has these right angles, this angle of 45 degrees plus minus. So this angle at the intersection of the curve with itself is always right. So the angle is always this. So what depends on the parameter A, the parameter A simply defines how big this curve actually is. And as a result, we have something interesting. You are not required to remember this. This is simply an example of how we can use polar coordinates to analyze some situation that would be very, very difficult in Cartesian coordinates. How can we understand this in Cartesian coordinates? That would be rather difficult to understand. But if we translate it into the polar coordinates, then it becomes easier to do. As I said, I'm not requiring this from you in examinations or tests. It's just an illustration why polar coordinates are good and what they can be used for. In the
You mean you don't want us to show the graph? That's what you mean?
Yes, you won't have to do much with polar coordinates in a test. Mostly we will be concerned with very specific other things. If you have polar coordinates, it might be something simple like, for example, take a point, translate it from Cartesian coordinates to polar coordinates or backwards. Nothing more complicated. All right, let me check. We have some 18 minutes of the lecture time remaining, so it's just as good that we might start considering perhaps equations of a straight line in plane. So we have considered now the Cartesian coordinates, we have considered polar coordinates, so different things, and now let's just consider curves or lines. In this case it will be straight lines in regular, normal Cartesian coordinates. So the more or less exotic part is finished for now, and we are moving on to the equation of a line in coordinate plane. So in fact, line in 2 dimensions. So how do we know that we have a line strictly defined? What do we need to define a line? We might have, for example, from school geometry, hopefully you remember that if we have 2 points, then we can draw one and only one line through these 2 points. That's for sure. So we might have an equation of a line if we know 2 points on this line. We might be able to get an equation for that line. But the approach we will be using is more like having vectors. And this will work exactly in the same way with vectors when we deal in 3 dimensions, with lines in 3 dimensions. In other words, if I have a point in the plane and if I have a vector telling me in which direction should the line go, I can again draw one and only one line through the given point in the given direction, because that's one of the most famous rules in geometry. That's Euclid's fifth postulate, that if we have a line and the point outside that line, then we can draw one and only one line through this point parallel to that line. In this case, we are not concerned with lines as themselves. We are, let's say, we can use a vector. If a vector gives us a direction, this means there's one and only one line that we can draw through the given point in that direction, and that's it.
But how you find the gradient for the equation if you use that?
Well, we will come to that. We will come to that. This is a huge topic, and I'm just beginning it.
Okay.
So, dealing with equations of a line. You are so impatient. Let's suppose we have a point on the line, and let's suppose we have a vector parallel to the line. And we will also consider a point. We will say, okay, suppose we have a point, a random point R on the line, or the current point, we could say, or the running point. You could understand what the R stands for. In other words, in this case, R is the absolutely random point on that line. We are assuming that we know the point M, the red point, we know the coordinates of the point, and we know this direction vector S that tells us in which direction to draw this line. We will start from this kind of situation, and then we will see how we can get all the other possible types of equations of a line from there. And so this point R, any random point on this line, so what we can see is that evidently the vector MR is collinear to the vector S. That's for sure. So if it's collinear to S, we can actually, well, we can write it as this. So XY is the point coordinates, they are the point coordinates that change. X and Y will be different depending on where we have this point. But X0, Y0 are known coordinates of a point that we actually know. We are assuming that we know those two red things, the point M and the vector S. And then from there we will get some quite interesting things. So, for example, if these two vectors are parallel to each other or collinear to each other, remember the rule of collinearity. Two vectors are collinear if and only if the coordinates are proportional. We had the check for collinearity, even in your vector test. So two vectors are collinear if the corresponding coordinates are parallel. And if the corresponding coordinates are, for vector MR, it is x minus x0, y minus y0. And for the vector S, they are numbers m and n. Then obviously we can write the proportion. We can write this proportion. So the vector MR that runs along the line in this direction, or perhaps in the other direction, it doesn't matter because the collinearity is still in force. So parallel, they still are parallel or anti-parallel, that is collinear. As long as I can write the vector MR as some number times vector S, or if we like, we can do it in this form. So this is the first equation of a line. This equation can be used if we know a point and the direction vector. That's one equation for the line that we can know for sure. So if you are given a point and a vector, and you are asked to write the equation of a line passing through this point parallel to that vector, this is what you write. So through given point in given direction. For this, there are two things that we know that we can read of this equation. First of all, if we see this equation, we know immediately one point on this line, and we know immediately a direction vector for this line. We know two things. So see, in the denominator, we see two numbers. They are the coordinates of the direction vector, no matter what. And x0, y0, the numbers subtracted from x and from y, are the coordinates of one point on the line. So in this form, if you see an equation, you immediately know two things. You know one point and you know the direction in this particular form. Now, let's suppose we have 2 points. Instead of the direction vector, we have 2 points on this line. No direction, but 2 points. So what can happen here? What can happen here is, well, evidently we could say, let's take this instead of x0, y0. We will use x1 instead of x0 and y1 instead of y0. So we will take this point as the point that we know. But where do we get the vector? Well, evidently, we can use the vector m1, m2, because it does point the direction. It does point the direction. So we say, okay, let the direction vector be actually the vector m1, m2. And that is, of course, x2 minus x1, y2 minus y1. And now, if we simply take the first formula, the first equation, and simply put in, instead of x0, y0, let's use the coordinates of point m1, because this is, after all, it is a point on the line. And instead of the vector mn, well, we have a vector mn. We have the vector from m1 to m2 that works as the direction vector. So what would the equation look like? It looks like this. Instead of x0 here, we have x1 and y1 instead of y0. And instead of m and n, we have our new direction vector. x2 minus x1, y2 minus y1. So this is called the equation through 2 points, or we call it sometimes the point-point form of a line. Point-point form of a line. The equation through 2 points. So now we have two equations. Can we build another one from all this? If this second equation looks rather complicated, so how do we know where we put x1, x2, and so on? In the end, remember that x1, x2, y1, y2 are just numbers. So after simplifying, it would still be in this form. But now let's see. If we multiply both sides of the first equation now by the number n, for example, that is, we are supposing that n is not 0, because otherwise it makes no sense. If n is not 0, then when we multiply both sides by n, we get something like this. So if we multiply this by n, we get y minus y0. If we multiply this side by n, we get n, and n is in the denominator still, and we multiply by the difference x minus x0 still in this form. And then n divided by m is some kind of number, evidently, because n and n are numbers. So as a result, we now have something more familiar. But there is also an aspect that I need to consider, and this aspect would be the angle formed by the vector s and the positive x-axis. So what we have here, we understand that n divided by m is actually tangent of the angle alpha of this angle. That's one thing. This is the tangent of that angle that the line, or in this case the vector, forms with the x-axis. This is the tangent. If we denote this tangent by some value k and call it the slope, so this actually is what happens when we get rise over run when we are plotting lines into coordinates. Rise over run, that is, the rise is n and the run is m. So in principle, when we discuss this rise over run thing in our elementary mathematics, then basically this is directly connected. This is directly connected to what we have there. So yes, it's the tangent. And if we simply rename it k, so instead of writing n over m, we simply say, okay, let's call it k. Then what we have is, here we see how the slope is rise over run. If I want to plot a line, all I have to do is decide what is rise, what is run, and I can build this staircase and get many points on the line. Rise, run, run, rise, run, rise, run, rise. And then, of course, I can draw the line without calculations. And so we end up having an equation like this because we simply substituted this ratio by k. K is called the slope. Yes, it is the same as rise over run, and yes, it is the same as the ratio of the coordinate of direction vector. So now we have the point slope form of the equation. If we know one point and the slope that will be the tangent or rise over run, we can write an equation of a line in this form. So depending on what we have and what we have not, we create the equation from what we have. There are actually, in general, there will be 7 types. We won't have time for 7 types today. I think one more and that's it. So we have through 2 given points, or we could say the point-point equation. Now we have the point-slope equation, and we also see that the slope is actually n divided by m, or rise over run, for the line. So everything, as you can see, all these equations, by the way, as you see, they are connected. We started considering the vectors, and we ended up building a number of equations for the same line, And so one more, if we open the parentheses, remember that this is a number, and this is a number, and this is a number. So if I open the parentheses, I have y, which is a variable, equals kx, yes, but everything else will be numbers. So we can say that b is y0 minus k times x0. That would be the b value if we combine the just numbers, because these are all just numbers. Then we get the explicit equation, the one that you consider in most cases at school, school calculus, for example, the classical equation of a line in the slope-intercept form. Slope-intercept. So k is the slope. The tangent, it's also the tangent, yes, it's the tangent of that angle, and it's called the slope. And b is the y-intercept. Do I have anything else? Yes. If x is 0, then y is b. That means b is the point on the y-axis. So this is called the this is called the y-intercept. Y-intercept. That is the point where the y-axis intersects or catches the line. In principle, as we already saw in elementary mathematics last week, I believe, It was if we have the y-intercept, this is the point B in the y-axis, always for this line, and if we have the slope, rise over run, if we know the slope, then we can say run and the corresponding rise. Again, run and the corresponding rise. So we can actually sketch the line without calculations. Without calculations. If you understand what fraction we have with k, and if we understand that B is the point of the y-axis, we don't have to compute separate points. We can simply go and count the squares in the system of coordinates. Okay, that's, yes.
So in a test, right? I know we could use both 3 and equation 4 to find the equation of the line. But I want to know, is there like, will there be a time where you need to use 3? Because I know if you use both to get the equation of the line.
Equation number 3, this point slope form, yes. That will be in calculus when we deal with tangent lines at a given point. We will get slope from the function, and we will have a point at which we are drawing this line, so we will need them, yes. This is important for calculus, we will have it.
Okay, but both 4 and 3, both of them could be used for the same purpose, right? Because you could just insert the y values to find the find b, and it's the same. But with the 3, it will give the equation one time, but in 4 you have to wait. You have to get the value, then add it into the equation.
The purpose is always the same, to get some kind of equation of a line, and after that we can transform it and simplify it as much as we can. This is basically not so much because of the purpose, but what we have got. We work with what we have got. If in a certain problem you have got 2 points, then you use those points to create an equation and simplify. If you have got the intercept and slope, you use those 2 things to create an equation. The thing is that these equations are for the purpose of we use what we have. And then, yes, there are different ways of doing it, because all these equations, they describe the one and the same line. This is all about the same line, different ways of describing it. What we use is what is the most convenient at that situation, as always. So you start with what you have got. If you have got 2 given points, very nice. We have this framework in which we put the coordinates of the 2 given points. Then we can simplify it as much as we like. And that's it. So the purposes of the 7 different equations of the line is so that we can use, in any situation, we can use those facts that are given. And the purpose depends, of course. Which form you want in the end will depend on what your task is. Okay, so we are 2 minutes past 4. It's time to finish. So I guess I will see some of you in half an hour for the retake of the linear algebra test. And I also assume that some who have missed the vector test on Wednesday will have the opportunity to write it afterwards at 5:30. All right, so for the rest of you who have everything set and everything okay, I'll see you on Monday. Have a nice weekend, and those who are retaking a test today in half an hour, or maybe in more than half an hour, depends on which test, it will be the same link. It'll be the same link. So those who only need the vector test, don't come too early because we will still be dealing with the first test. But, well, don't come in the last possible moment either. Okay, I hope everybody has remembered to write their name in the chat so that I can deal with the attendance.